Hi and Assalamualaikum. My name is Muhammad Izzat Darwish bin Muhammad Azmi, and I'm from class IAC 5P. So today I'm going to show you exercise 1. The goal here was super basic to build a simple program in labview that simulates a sine wave and then uses a slide control to trigger an alarm light if the wave get too high. So first thing first, all we need to do is we need to get a while loop from the structure part. Then the next step, we need to get a comparison block, comparison block to put it inside here. Then set it to greater and second signal input. And the next one we need to do is simulate signal. We need to get the simulate signal block, and we need to set the amplitude to 10, and we need to turn on the simulate acquisition timing. Alright. Next, we go to the front panel. We need to get the numeric vertical pointer slide. Vertical pointer slide. Then the next one we need to get is the round LED. Round LED here. And these two need to go inside the while loop. Okay, so here at sign, I need to create a graph indicator for the sign, and uh, a stop button is needed. Then next step is we just need to connect the wire. So the boolean part need to go to the result, and the slide part need to go to the operand one, while the operand two go to the sign part. So next we go to this property. Then we need to show digital display and change the slide to limit. Change the slide to limit. Okay. Need to move it a bit here. Alright. So now now we can start to run the program. So uh, on the front panel we put a slide. We put a slide, round LED, stop indicator, and a sine wave. Right. So the key part here was the comparison block. It constantly asks if the signal value is greater than the limit value. So here I'm gonna set it to 5 first, right? So that you can see it easily. So if the answer is yes, the wire send a true signal to the LED and it light up. So when I run it, if I set the limit to 5, which is here is 5, the LED flashes. LED flashes whenever the wave goes above 5. So as you can see here, that right now the wave didn't hit the five yet. So the LED still off, and when the wave hit the five, then the LED will turn on. So now the LED will turn on. All right, and then it will turn off again if the wave hit five another time. So this keep on repeating until we press the stop button to stop the simulation. So this simple setup is exactly how real monitoring work. Think about, for example, like a factory machine. The sine wave is like the vibration level from a motor. The limit is the maximum safe vibration level you set. If the vibration or signal goes over, which is here, which is signal, goes over the limit, so the alarm light will turn on, telling an operator to check the machine before it breaks. So in summary, this exercise is what I learned is the fundamental structure of LabView, how to use the front panel, and block diagram panel for wiring logic inside the while loop. Successfully implemented a basic monitoring system where a comparison function check if a simulated signal exceed a set limit to trigger an alarm LED. So the main challenge here that I faced was that the program ran too fast to see the wave move. So I solved this by learning to use the highlighted execution features, which is here, the light bulb here. So if I turn it off, we cannot see how the system work or move. But if we turn it on, we can see it moving. So I think that's all from me to explain about the exercise one. Thank you. So now we're gonna move to the exercise two, which is data acquisition in LabVIEW without the hardware first. So the purpose of this task was to learn how to interface a LabVIEW with the data source. For this case, we are using a simulated device to acquire a real-time data, analyze key static from that data stream. So and finally, we save the result to a file for later review. So this exercise involved setting up the environment first and then building the analysis VI. So before programming, we had to create a virtual sensor using a measurement and automation explorer, which is Max. So we created an NIDAQ simulated device, and this step is crucial because it allows us to develop and test our code logic before we ever connect to the physical hardware. So now I'm going to show you how to do it. So first step, we need to open the Max software. Then we need to right click here and create a new file. Create a new. Then we're going to go to the simulated knee DAQ MX and double click here. Then we need to find a 6221 PCI 6221 here and double click it. So if the display is like this, we need to right click here at the NIPCI 6221 and test the panel. Alright, so on the mode, we need to change it to the Fini and we can start. So this is the test panel for NIPCI 6221 for exercise 2. So next, we need to go to the lab view to do the VI logic, to build the VI logic. So first thing, we need to take the while loop first, and then we need to find the DAQ assistant. For the DAQ assistant, first click the acquire signal and analog input, then voltage. So here we need to choose the AI0 and click finish. Then here you just need to change the acquisition mode to continuous sample, then click OK. So first we just right. So here we need to create a graph indicator for the AQ assistant. Next thing we need is a timer, time delay here. So set the timer to a 0.1 to a 0.1. Then the next thing we need to find is at here first find express, then signal analysis, then get the statistic. For statistic calculation, you just need the arithmetic mean. For extreme value, we need the maximum and the minimum. Okay, so the last component that we need is the express and output and write missed file, right, measurement file. So here, this is the file name that it going to save on later on our computer. So first we need to save to series. Then for segment header, we need a one header only. And for time, we need one column only. Then okay. So next we need to connect all of these wires so that it can display, it can run perfectly. For arithmetic mean, maximum and minimum, we need to create a numeric indicator for each of them. Indicator. Create numeric indicator. So once all of the wire have been connected, we just need to use this button, which is a cleanup diagram, so that it will arrange for us. And the last one that we need to find is here, this one, which is a stop button. Then we go to the front panel and arrange it. So let's arrange it first before we try to run. So okay, we place a while loop and added a time delay express and set it to 0.1 because we want the loop to pause, which slow down the data acquisition enough for us to see the graph update clearly. So we use a DAQ assistant inside the loop to configure it to continuously read analog input voltage from our simulated device. Then the analyzing stream, we insert the statistic express. So this block process the incoming data stream and calculate the arithmetic mean, maximum, and the minimum. And the displaying result, we create a numeric indicator for each of them. And the logging data, which is this block here, write to measurement file, is it function automatically collect the data and write it to a file like a CSV and a spreadsheet when the VI is stopped running. So now we're gonna run it. So we just need to run it for a bit. We don't need to run it for a long time. Next, we go to this file here, and this is the file, the test001.im. This is the data from the front panel. Then we need to open the Google Sheet and click here, blank spreadsheet, open, file, upload here, then download the file. So once the file has been downloaded, we can open it on Words or Notes or Excel. But now I'm going to show you on the Word first. So as you can see here, that it has a time, date, time, the username, and the X value and the voltage for each of the sine wave that it have on the LabView VI diagram. So we go back here. Alright, so I think that uh, if this was a real-time system, the DAQ system would be reading live data from a sensor measuring vibration, temperature, or flow. So the statistic VI constantly analyze the stream. For example, an engineer might set an alert if the maximum temperature reading exceeds a safe limit. The write to measurement file function create the official logbook. Engineers use this log to track machine health over week or month to predict a maintenance needed. So in summary, for exercise 2, what I learned was how to manage the streaming data, which is data that arrives continuously rather than all at once. I learned the standard workflow for data handling, which is acquire, analyze, and log. So the main challenge was that the loop ran too fast to see the data moving. I solved this by adding the 0.1 second time delay inside the block diagram. So it allowed me to visually confirm that the DAQ assistant was reading data and the statistic VI was calculating the result correctly. So I think that's all for now, which is the exercise 2. Alright, so now I'm gonna explain about exercise 3. So for exercise 3, we will learn about hybrid programming. So the goal was to make our graphical level code and insert a block where we could write text code specifically using script node to apply a moving average filter to clean up a noisy signal. So I'm just going to show you the recording because I have done it on my school PC. So I will show you how to do it first. I will show you how to do it while telling you what do you need to do. The step. Alright. So first step, we need to find a while loop inside the structures. Okay. Next, we need to find a math node inside the structure. After that, we need to put the code inside the math node. I have copied the code earlier, so I'm just going to paste the code. So as you can see here, that the code is n equal to 0 to 100, s1 equal to cos 2 times pi times f low times n, while s2 is cos 2 times pi time f high time n. So the input signal equal S1 plus S2 equal to 1, 1 comma m. Output signal go to filter num1 input signal slash m. So next, we need to create an input and output for them. So the input here is on the left side, while the output was on the right side. So the input is F high, F low, and M, while the output is S1, S2, F low for the input, and the last one is M. Okay, so next one is the output. We need to create an output which is S1, S2, and input signal and output signal. Right, so for output, we need to create an indicator, while the input, we need to create a control. So we can change the value of F high, F low, and M ourselves. We can put any number that we want. So the next thing that we need is a time delay. So we need to find a time delay first, and then set the time delay to 0.1. Okay, and the last block that we need is a control block that can stop the system from running. Alright, so after we have filled up the number for F high, F low, and M, we can run the code. First, oh, sorry, we need to put a breakpoint first on input signal and the output signal before we run it. So now we run the program. So if you want to see the result, we need to right click on the math node and select probe. Then we need to click on the step over line so that we can get the variable value on the math script node. Okay, so now I will show you the value for F high, F low input signal, M, and num output signal S1 and also S2, as you can see there. That's the output signal, and then S1, and final one is the S2. So, alright, so this is how engineer handle tough math. So if you have a complex formula for filtering sensor data, it's easier to type it into the math script node than to build it out of hundreds of tiny graphical blocks. So it let us use a powerful text-based math right inside our visual program. So what I learned is how to mix the text and graphic. The biggest challenge was making sure the variable name match exactly between the text code and the graphical output terminal on the node border. So this exercise shows us how to apply advanced signal processing easily. So I think that's all for me for exercise 3. Alright, so now for the last exercise, which is exercise 5, I'm going to explain about the remote panel. So the goal was to take the data acquisition program that we built from exercise 2 and make it controllable from a web browser, like controlling a machine from your phone or laptop or any devices. So this exercise is about publishing the VI. So now I'm going to show you how to do it with the recording that I have made on the school PC. Right, so if we start, we need to open the exercise 2. So we need to run it for a bit so that the data will load inside that. Alright, then we stop the running. Then we go to the tool and go to the web publishing tool. Then select the VI name. Then next. Next, we need to put the document title, which is, as you can see, that I put it as a data monitoring. Then you can put on the header and footer that you like. So if you didn't want it, just leave it there. So this is the URL. So next, you just click connect. Then here you can see that this is on the web browser and we can control this data monitoring. You can see the arithmetic mean, maximum and minimum value from other devices. Alright, so when we control it, that is the key part, because to actually use the control, to control this, we need to right click and request control of VI, as you can see there. Then as long as the original VI was running on the desktop, we could then click the run button or change the setting right there inside this browser. So you can do it as long as the original VI on the LabView still running. If it's not, then you cannot run it. So in real world engineering application, this is a huge for remote maintenance, because if a machine breaks down miles away, an engineer can securely log in via a web browser to check the status, restart the process, or change a setting without having to physically go to the machine. So what I learned is how to publish a VI for a remote access. The biggest challenge was making sure the web server was running and the original VI was actively running on the desktop. Once those two things were set, we could successfully request control from the browser to run the program remotely. So I think that's all for me. I have explained all of the 5 exercises. So thank you.